So we continue with the angular speed. Let's again consider the case of this particle P that is moving through a given angle from the initial position A to the final position B from time t initial to time t final. So there is a change in the angular position as we have seen in the previous slide, which is given by delta theta. However, this rate at which delta theta occurs can vary, which means that the time needed for this variation to happen, it can be small or it can be large. If the rigid body spins rapidly, delta theta occurs in a short time interval. يعني إذا كان عم يبرم كثير بسرعة, هل variation delta theta could be occurring in a very, very small amount of time, while if the object rotates slowly, then delta theta can be occurring in a longer time interval, or ممكن يكون بدها وقت أكثر بكثير من الحالة الأولى لحتى يصير في هال delta theta variation. So the rate at which the angular displacement is occurring, this is what defines the angular speed. And so if this is happening during a given time interval delta theta, then we talk about the average angular speed, which is defined by the ratio between delta theta and delta t, where delta theta is the variation in the angular position and delta theta is the time interval during which this variation has happened. So the average angular speed is given by omega bar or the omega average. Both are valid. Now, let's move on with the instantaneous angular speed. If we are not looking at a given time interval, which is quite defined, but if we are looking at a very short time interval in such a way that delta t approaches zero, then in this case, we don't talk any longer about the average angular speed, but we consider the instantaneous angular speed, which is in this case defined by the derivative of theta with respect to time, and omega has units of radians per second. And this is kind of obvious because the unit of omega is the unit of theta divided by the unit of time. Unit of theta is the radian, unit of time is seconds. So all what you need to know from this slide is that the average angular speed is given by the ratio between the delta theta and delta t, while the instantaneous angular speed is defined by the derivative of the angular position with respect to time. And in the same way, we can define the angular acceleration. So let's start by the average angular acceleration, which is defined as the ratio of the change in the angular speed to the time interval delta t during which this change has occurred. And so alpha bar, it's defined as omega final minus omega initial, omega final minus omega initial divided by t final minus t initial. So it's nothing else than the ratio delta omega over delta t. And again, if we are not looking in a given time interval delta t, but we are looking at some instant or some moment time t, which means that when this delta t approaches zero, then the limit of this ratio, the limit of the ratio delta omega over delta t when the time interval delta t approaches zero, this defines the instantaneous angular acceleration, which is defined by alpha. And by definition, this limit is nothing else than the derivative of the variable omega with respect to time. And so this is why we define the instantaneous angular acceleration by the derivative of omega with respect to time. And again, the unit of alpha is given by the unit of omega divided by the unit of the time t. So it's given by radian per second divided by second. So it is given by radian per second squared. And so this is it for the angular variables. Just want to remind you from the previous chapters that whenever you are dealing with angular speed without the word instantaneous, that means that you're referring to the instantaneous variable. And whenever you're dealing with the angular acceleration, also you have to deal with the, you refer to the instantaneous angular acceleration. So for the instantaneous angular speed and angular acceleration, we do not use the word instantaneous. However, when we want to study or discuss the average variables, then we will use average angular speed and average angular acceleration. Now, we have seen that this is just a ratio. I mean, alpha is a ratio between omega and time, and also omega is a ratio between theta and time. So are these quantities vectors or not? In principle, we can say that they are not vectors, but by just looking at the equations. However, this is not true, because if you look at this disk, for example, which we have considered previously, we said that this disk is making a rotation about some axis that passes through the point O, which is the point in the middle. Now, since this rotation can occur in two directions, so clockwise or counterclockwise, that means that the rotation, it has a direction, and this direction is defined by a sign, basically. So if it is clockwise or counterclockwise. Now, how can we determine the vector omega? So by this, we can immediately deduce that the angular displacement, the angular speed, and the angular acceleration, they are vector quantities. But how to define their vectors? This is the best way to define their vectors using the right-hand rule. إذا كان عندنا هيدا الديسك عم يبرم ب let's say بهالاتجاه هيدا in the clockwise direction. Okay, بنقدر نقول إنه it's vector omega, the direction of the angular speed points downward. How can we know this? It's very easy. You use your right hand and you apply the right-hand rule. الأربع أصابع مثل ما نكون شايفين على الصورة بتحطون بنفس اتجاه البرمي وبتطلعوا على إصبعكم الكبير بأي اتجاه هو. إذا كان اتجاه لتحت فإذا بتحطوا الأوميجا pointing downward. أما إذا كان الاتجاه المعاكس لهون، يعني إذا كان الديسك عم يبرم counter clockwise بالاتجاه الثاني، خلينا حتى نستعمل الأزرق. إذا كان عم يبرم بهالاتجاه ساعتها فكنتوا تحطوا أصابع إيدكم الأربعة باتجاه البرمة، حتلاقوا إنه إصبعكم الكبير حيكون pointing upward. فإذا كان الديسك عم يبرم بهالاتجاه الأوميجا بتكون لفوق بدل ما تكون لتحت. Okay. Another two figures that may help you also in understanding how we can use it. Look, بهالحالة نفس الشيء، الأصابعنا الأربعة بنفس اتجاه البرمة واللي هي بهالحالة counter clockwise بيطلع معنا الأوميجا لفوق. بتاني كيس بنحط أصابعنا الأربعة بنفس اتجاه البرمة اللي هي هون بهالحالة clockwise، فبيطلع معنا إنه الإصبع الكبير اتجاهه لتحت، and so we deduce that omega points downward. So this is the best way and the only way to determine the direction of the angular speed using the right-hand rule. Now, let's move on to a new section. This is a very important section because it's one of the simplest cases of the rotational motion in which we have a motion or rotational motion under constant acceleration, constant angular acceleration, of course. So in this case, actually, we can derive exactly the same kinematic equations that we have previously derived in the case of a uniformly accelerated rectilinear motion. So in the case of a translation with a constant acceleration vector. However, so we are not going to derive them. We are simply going to guess them to make an educated guess من خلال بس هو equations. يعني هن عمليا هن ذاتهم equations طلعناهم سابقا، بس الفرق الوحيد انه لازم بدل ما نحط كل variable linear variable نستخدم the corresponding angular variables يلي بتلعب دورة. So let's start by the very beginning. نحن بحالة اللي هون بحالة اللينير يعني نحن بنعني فيها translation. بحالة translation we have defined different variables, and these variables they are the position, displacement, the speed or the velocity, the acceleration. And then when we said then when we have a constant acceleration, we can derive these different equations. So v as a function of time, x as a function of time, v as a function of x, and we have also seen one more, which I don't put here in this table. So let's see what are the angular equivalent of these variables. يعني بدل ما يكون في عندنا هون الvariable position x، equivalent تبعها هو theta. Displacement equivalent للدلتا x هو delta theta. And we have seen that instead of talking about v, now we're talking about omega for the angular speed. And instead of talking about the acceleration a, we are talking about the angular acceleration alpha. So we can then say instead of v, we will have omega. Instead of a, we will have alpha. And instead of x, we will have theta. And so let's make this substitution. So شو بيطلع معنا من هون؟ بيطلع معنا بدل ال v رح نحطه omega is equal to omega 0 plus بدل ال a رح نحط alpha, so we end up with alpha t. And so this is the equation for the speed as a function of time, omega as a function of time. For this equation here, we are going to do the same. So instead of x, we will have theta. So we'll end up with theta equals to half alpha t squared plus omega 0 t plus theta 0, which we have here on the right. And the same for the last equation. So omega squared minus omega 0 squared is equal to 2 alpha theta minus theta 0. And so this table is quite important because it tells you all the equations that are relevant in the case of translational motion under constant acceleration or rotational motion under constant acceleration. And we are not going to derive all these equations, but if you want to derive them, they are very easy, and you use exactly the same procedure we used in the case of translation to derive these the set of equations. Now, is there a relation between the linear and the angular quantities? So in other words, we have seen that in rotation motion, we describe the rotation through the angular position theta, and from this angular position, we have defined both the angular speed and the angular acceleration alpha. Now, can we relate these angular quantities with at least, for example, v, the velocity that we know from the previous chapters, the acceleration a, and here instead of x, I will put s, because s is more suited to be used in this case because it describes, or it defines the length of the arc of circle traveled by the particle. يعني هون ما كثير لها معنى نحط x لانه البارتيكل ما عم تمشي on a straight line وانما عم تمشي along a circle. So instead of x, we are going to put s. Is there a relation between these two sets of variables, the linear variables on one side and the angular variables on the other side? Well, let's consider this case. We have an arbitrary shaped body, rigid body, that is rotating about the axis that passes through O. So this is the axis, it's perpendicular to the page, passes through O, and this object is making a rotation counterclockwise. Now, if you consider the point P, we have said earlier that the point P is moving along a circle. And this circle has a radius r, which is the distance between the point P and the axis of rotation. And we know from the previous chapter that if a particle is moving on a circle, then the linear velocity is always tangent to the circle. So the velocity of the point P at any time is always in this direction. So it's tangent to the circle described by the point P. Now, how much is the magnitude of this tangential velocity? We have seen that the magnitude of this tangential velocity هي عمليا the derivative of s with respect to time. يعني هي قد ايه عم تمشي البارتيكل on this arc of circle in a given amount of time. But since we are looking at the instantaneous value, we should take the derivative of s with respect to time. Okay, that sounds great. Now, how much is s? So we have seen previously that s is equal to r multiplied by theta by definition. So we replace s by r theta. And we can, since r is constant, this is the radius of the circle, we can get it out of the derivation because its derivative is simply 0. And so we end up with r times d theta over dt, which is the derivative of theta with respect to time. But since this we define it as the instantaneous angular speed, we can therefore deduce that the tangential velocity is equal to r multiplied by omega. And so this is the first relation which relates between the linear speed and the angular speed, between v and omega. Let's now continue and try to find the relation between the linear and the angular acceleration. Okay, since we have here a point, a particle P, which is defined by this point, that is moving along a circle, again, we have seen in previous chapter that the acceleration vector of this particle P, it is composed of two components, basically. It includes the radial component, which is always along the radial direction and pointing towards the center of the circle along which the particle is moving. And it also includes another component, which we call the tangential acceleration. And this is responsible for the variation of the magnitude of the velocity as a function of time. So we have previously seen then that the tangential acceleration is defined as the derivative of the speed with respect to time. And this speed in this case, v, is nothing else than r times omega. So if we substitute v by r omega, and again, the derivative of r with respect to time is equal to 0. So this we can get it out of the derivative. أو بكل بساطة فينا نقول إنه هيدي عمليا هي derivative of r omega with respect to the time is nothing else than the derivative of r with respect to time multiplied by omega plus r multiplied by the derivative of omega with respect to time. Since this is equal to 0 because the radius of the circle is constant all the time, then we can write this as r multiplied by the omega divided by dt. And this is nothing else than alpha, as we have seen in the previous slides. So we can deduce that at is equal to r multiplied by alpha. So this is for the tangential component of the acceleration. Now, what about the radial component of the acceleration? We have seen also in the previous chapters that the magnitude of the radial component is the same as the centripetal acceleration. And so we can write AR as v squared divided by r. But because v is equal to r multiplied by omega, then we can write AR as equal to r squared. So it's r times omega squared divided by r. So we end up with r squared omega squared divided by r. And so this reduces to r multiplied by omega squared. And so we have to know these two equations. First of all, that at is related to alpha through at is equal to r alpha. And finally, we also we know that AR now is equal to r multiplied by omega squared. So the total linear acceleration vector for a given particle described by the point P is composed of both radial and tangential components in the following way. And the magnitude of A is then given by square root of AR squared plus AT squared. So it's a square root of r squared alpha squared for AR squared plus r squared omega to the power 4 for AT squared. And if we take r squared in common, and we get it out of the square root because it's r squared, we end up with r multiplied by square root of alpha squared plus omega to the power 4. So this is it for the relation between the linear and the angular quantities.